Now that we have done the regression, we would like to look at the coefficients and tell whether or not they are different from a certain value, for example 0. So to do this, we can calculate the t-stat, and you remember the t-stat from when you estimated the difference in proportions and difference in mean, and we do the same here. Okay. So, for example, we take the our t-stat is the sample statistic, for example, B0 or B1, and just subtract the value of the hypothesis. And if we want to check whether or not the value is different from 0, then this would be 0, for example. And we measure this distance in terms of the standard error of the sample statistic. Okay. So for example, if our null hypothesis is that the true slope is equal to 0, that the x variable does not contain any useful information for predicting the y variable, then the alternative hypothesis would be that the true slope is different from 0. In this case, we would calculate the t-stat as the coefficient we get from running a regression on a sample, coefficient from sample, and we deduct the cutoff value, and we measure this distance in terms of the standard error, right? And this would be the population slope. Okay. And instead of measuring the difference from 0, we could measure the distance from, for example, any cutoff value, for example 4, and you could make the test a one-sided test. And here we have a one-sided test. We wonder if the slope is greater than or equal to 4, and the alternative hypothesis would be the if it's less than 4. Okay. If it's less than 4, then we would implement the model, right? So the t-stat would then be the coefficient and we would subtract 4 from the coefficient, and this would be the standard error of the coefficient. Okay, and likewise you could have a two-sided test, whether or not the intercept is different from 2, and the null hypothesis would be that you can't tell if it's different from 2 or not. So the t-stat would then be the beta 0 or b0 minus 2 divided by the standard error. And you would of course, look at the number of observations to get the degrees of freedom to compare the t-stat, or compare t-stat versus the critical value. Okay, a typo again. Let's see. Versus the critical value. Okay. So for example, let's have some numbers and use a t-statistic to to determine if the slope is statistically significantly different from 0 at the 5% level. Okay, so for example, we want to look if it's different from 0, okay? Which means that the alternative hypothesis is that the population slope is different from 0, which means that the null hypothesis would be that the population slope is equal to 0. Okay, so that would be our hypothesis. And then we could look at the t-stat, the absolute value of the t-stat, because it's a two-sided test. It would be our coefficient for the slope minus the cutoff value, it's 0, divided by the standard error of the coefficient for the slope. Okay, so for example, in the Bucket-Hansen example, we have the slope from our regression output, because we ran this regress sales on foot traffic, and the slope is 23.672 or 673. 23.673 minus 0 divided by the standard error of B1. And luckily, the statistics program does that for us. It's 2.431. So it's 2.431. That would be the standard error of B1. And this would be 9.74. Well, we don't need these, actually. Okay, so that would be 9.74. So what we know from what we know now is that the value of the slope, the coefficient value, is 9.74 standard errors away from our null hypothesis. Okay, which is that, let's see, if we just do this, if we make the hypothesis here, we would like to find the in 95% confidence interval to test whether or not our B1 is different from 0, and that would give us, let's see, 2.5% in each tail. And how many standard deviations away from the mean would we have to go to cover 95% of the area? Here that would be the B1 value we got. And what we can do is we find the critical value in the t-table. Let's see if we have the t-table here. And what we want to do is we want to find the area under the curve, which corresponds to 95% of the area, because we want to be 95% certain to include the true value of the slope, which means that we are looking at the 5% significance level, and we have a degree of freedom of n equals 80. We have 80 samples, minus 2 because we are estimating 2 coefficients. So we use up 2 degrees of freedom. And here we have degrees of freedom, df, but we have a degree of freedom of 78, which is 80 minus 2. So our degrees of freedom is 78. And here we have degrees of freedom of 75, and we have a degree of freedom of 100. And we take the closest lower degree of freedom to be certain to include our true value with a certain probability. And if we look here, the tail distribution for degree of freedom is 75, to get 2.5% in each tail, or equivalently 95% area in the middle, we have to go 1.992 standard errors away from our coefficient value. Okay, so what this means is that if we go plus 1.992 standard errors above B1 and negative 1.992 standard errors below B1, then we cover 95% of the probability that we include the true value, the beta one, in our confidence interval. Okay, but what we have found here is that we can, instead of making the confidence interval, we just compare our t-stat with critical value. And then we compare 9.74 with 1.992, okay? Which means that we are unlikely to get this result by chance, okay? So that's why we reject H naught. Okay? So, what is the p-value of the hypothesis test in part D? So the p-value, well, the p-value is the probability of getting a t-stat, absolute values, of greater than or equal to the t-stat that we got. So what would this probability be? It would be the probability of getting t-stat of less than -9, it should say. Let's see. 9.74 standard errors below our B1, plus the probability of getting t-stat, which is higher than or equal to our observed t-stat. And this is close to 0, and this is close to 0. So the p-value would be close to 0. Okay? And we can see that graphically if we just draw a normal probability distribution, and we go 9.74 standard errors away from the mean, and minus 9.74 standard errors below the mean, and the area under the tails is very close to 0 when you get that far out from the mean. And we can probably see that here with degrees of freedom of 75. If you go 4.11 standard errors away from the mean, then the tail distribution, or the area under the tail, is 0.00005, which is incredibly small. It's 0.005%. And we found a result of 9.74 standard errors, which means that the probability of getting this result is highly unlikely. Okay, and what we can do is that we can in this framework we can create a confidence interval around our estimates. Okay, so what we are doing is that we can let's see here, if we have the sample statistic, for example the B1 or the B2 or B0, we can find the two-sided critical value from the t-table, and we have the standard error of the sample statistic, for example of B0 or of the B1, then you can find the, for example, 95% confidence interval by going a certain number of standard errors away from your observation, so such that the tails contain 2.5% probability, which leaves 95% probability here in the middle. So that would be the critical value, which is the number of the number sorry, the number of standard errors away from the mean you have to go to be 95% certain to contain the true value of the slope. So this would be the t 0.025, which is 2.5%, given number of observations minus 2, which and mean minus 2 equals the degrees of freedom. Okay, so this is the critical value. And for example, a 95% confidence interval for beta naught, the true value of the intercept is made equally. You have the same critical value, but of course the coefficient value and the standard error of the coefficient differs from the B1. Okay, and you can have a different confidence interval. For example, the 90% confidence interval. If you're okay with only being 90% certain that you capture the true value of the parameter, then 90% is okay. And what's different is just the number of standard errors you have to go away from the mean, or your coefficient. So here you have a different critical value. Okay, so for example, if you have degrees of freedom of 34 and you want the 95% confidence interval, which means that the tail probability should be 2.5% or 0.025, what is the number of standard errors you have to go away from your estimate? Well, then we can just go to the t-table again, and if you have a degrees of freedom of 34, we can see that in this table, and the tail probability should be 2.5%, which is here, which means that you would have to go 2.032 standard errors away from the mean to be certain that the tail probability is 2.5%. Okay, so that would be 2.032. So that would be from table it's equal to 2.032. Okay? And what is the 95% confidence interval for the slope in our regression model for Bucket-Hansen? Then we look at the B1 plus minus the critical value, times the standard error of our coefficient. Okay, and the critical value, it's the t of 0.025 given 78 degrees of freedom, and from table we found that yeah, we already found that actually. We found it here. It's 1.992. Okay. 1.992. Okay. So then we have the B1 coefficient. It's 23.673 plus minus the critical value 1.992 times the standard error of our coefficient, which it was 2.431, which gives us a range of 18.83 to 28.51, and that's the confidence interval. But what does it really mean? It really means that we are 95% certain. We are 95% certain that beta 1 is included in our confidence interval. Okay, because we know that with repeated sampling and we're making a 95% confidence interval for each sample, then 95% of those samples will contain the true value, the beta 1. So we are 95% confident that the beta 1 is between 18.83 and 28.51, but we're just 95% confident. We might have the true beta in this range or not. So we might be mistaken, but we know that in 95% of the instances we are correct, and in 5% of the instances we are wrong. Okay, so what is the 80% confidence interval for beta naught? Well, then we take the coefficient value for the intercept, and we have the critical value. The critical value in this case, it's the t 0.10, because if we have 80% of our instances in the middle here, we want to be 80% certain, then we are 20% uncertain with 10% in each tail. Okay, this would be better not, B not. Okay, so this has to be multiplied by the standard error of our coefficient, and we have from our result from stata, we have the coefficient value. It's negative 133.81, and we have the standard error of 94.584, and we can just plug it in, and this would be let's see, negative 133.81 plus minus, yeah, we need the critical value of course. So critical value from table, and we have degrees of freedom of 72. We need the 80% confidence interval. That would be, let's see, if we go to the T table here, and we're interested in let's see, this table, okay, because our degrees of freedom is 78 and 75 is just below that, and we want the we want to be 80% certain, 80% confident to include the true beta not, the true intercept, which gives us a tail distribution or tail probability of being wrong, with 10% chance of being wrong at either side. If this is okay for us, then we have to go 1.293 293 standard errors away from our B naught, right? So that would be 1.293 times the standard error of B naught, which is 94.58. 94.58, which gives us a range of negative 256, I've got it here, 0.1 to negative 11.56. So this is our 80% confidence interval, which means that we are 80% certain that the true intercept is captured by this interval. Okay, and let's see, we can use to test our hypothesis. We can use either the confidence interval or we can use the t-stat and compare with critical value, or we could look at the p-value, okay? And for a two-sided hypothesis test, the t-stat, the p-value, and the confidence interval test will all reach the same conclusions. Okay, that's for a two-sided hypothesis test. Okay, and the difference is between these is really about what kind of hypothesis you can test with them, or what you are actually testing. For example, the confidence interval gives you like a range of values in which you are quite certain the true value of the population parameter will be. Okay, and here you have really a list of all values you would reject or fail to reject. So for example, if H0 was here, then you would fail to reject it. Okay, you would fail to reject it. If H0 was here, then you would reject it. So all these H0 values here in the confidence interval, you would fail to reject. All the null hypothesis values outside, for example 0, you would, if zero was here, then you would reject it. Okay, then you would say B1 is or the true value of beta 1, the true parameter, is different from 0. Okay. Or if you use the t-stat, it tells you whether you reject or fail to reject only one particular hypothesized value. Okay, and this is often H0 equals 0. Okay, so the t-stat in our output is here. Okay, which this automatically tests for the H0 equals 0. Okay, that's important to remember, which means that the coefficient for foot traffic for the slope is 9.74 standard errors away from 0, whereas the coefficient for the intercept of negative 133, given a standard error of 94, it's negative 1.41 standard errors away from the mean. Okay, and the good thing about t-values is that you can quite easily check whether or not a coefficient is different from 0, because if the t-value here is 9, then you know that the most often the 95% critical value is around 2. So this is definitely statistically significant from 0, whereas the coefficient on the intercept is not, because it's only 1.4 away from 0. Okay. Let's see, where did we get? Yeah, the p-value. Okay, so the p-value gives you the smallest significance level, alpha, for which we can reject the null hypothesis. And you can see that from the output that the probability, the p-value, the probability of getting a value greater than this t-value, what does that mean? It means the probability of getting like a coefficient further away from zero, by chance is really small for this slope, okay? Whereas by chance you could get a more extreme coefficient by chance for the intercept in 16% of the times, okay? So that's the logic behind the p-value, the probability value. And next time we're going to talk about prediction intervals. Okay.